It's a pleasure to be here today to talk to you about the exciting activities in the world of multi-die and chiplets for AI chip development. I'll start with the semiconductor landscape and the importance of AI chips as the next growth driver for the semiconductor industry. Next, I'll talk about essential multi-die innovations to address the challenges of AI chip development. The importance of the ecosystem cannot be understated, and I'll end with a few comments looking into the crystal ball. In December 2024, WSTS, that's the World Semiconductor Trade Statistics, came out with a report which has been endorsed by the Semiconductor Industry Association, or SIA. And in this report, they said that these global semiconductor sales for 2024 exceeded $625 billion. That represents a 19% year-to-year growth. Further, they projected that in 2025, the industry, the global semiconductor sales, will increase 11% year-to-year to a number approaching $700 billion. It took the industry 6 decades to reach the $500 billion mark. It's expected that in a short 8 to 9 years, in less than a decade, the industry will double that. That's a staggering growth, an impressive growth. There have been a number of growth drivers along the way, which have helped the industry weather significant economic storms like the dot-com bubble, the Great Recession of 2007-2008, and of course the global pandemic. The growth drivers include the PC revolution that many of you are familiar with in the 90s, the internet boom, the mobile explosion, and more recently, the world of interconnected components and cloud computing. Today, we are in the era of pervasive intelligence and smart everything. System companies, as you very well know, are developing their own silicon. Hyperscalers, automotive companies, and so on. They are pushing the architecture, the technology envelope, the performance envelope, and they're differentiating versus their customers. Silicon and sensors are everywhere. There are a myriad of applications. Smartphones are relegating smartwatches are relegating traditional watches to be fashion statements. And then, of course, there is AI, artificial intelligence. Thanks to the significant breakthroughs in technology in this space, there is unprecedented investment in AI infrastructure, AI chips, as well as AI applications. More and more AI applications are driving the demand for improvements in AI infrastructure, in AI silicon, and AI accelerators, and in turn, the availability of enhanced AI infrastructure and AI accelerators is further driving more and more demand for and supply of AI applications. Indeed, it's in a self-enriching positive feedback cycle which is driving the growth in the semiconductor industry. It's expected that the AI silicon will account for $400 billion of global semiconductor sales by 2027-2028. That represents a 29% CAGR. You all are familiar with some of these AI accelerators and chips from keystone companies, like the AMD Instinct MI300, which has over 300 GPUs, the NVIDIA Blackwell AI Superchip, the Microsoft Azure Maya accelerator with over 100 billion transistors, Intel Gaudi 3 with 64 tensor processors, the Google TPU, which is in its 6th generation called Trillium, and so on. None of these AI chips would have been possible without multi-die. Take NVIDIA Blackwell GPU as an example. It consists of 2 reticle limited dies connected to each other at 10 terabytes per second interconnection speed. And it has over 200 billion transistors. Analysts estimate that the chiplet market will exceed $148 billion by 2028, which represents a staggering 85% CAGR. and $400 billion in 10 years by 2035. Of course, a lot of this growth is driven by the server and PC market, no surprise there, with healthy participation from automotive, mobile, networking, 5G, and perhaps 6G one day, IoTs, and so on. If you look at the top 5 distinct chiplet types, compute, which includes CPU and GPU, memory, networking, and sensors, analysts estimate that they will account for over $100 billion of semiconductor sales by 2033, which represents, again, an impressive 40% plus CAGR. AI chips are different from your general purpose CPU and GPU chips. AI accelerators are designed and architected to address AI workloads. AI workloads can be training or inference. An AI training chip has to address or process and crunch through lots of data, tons of data. They have to perform immense number of matrix multiplications, tensor operations, machine learning, real-time data processing, and so on. So the requirement there is large number of cores, high performance compute, and of course, high memory bandwidth. In contrast, an AI inference chip takes in a new input, uses a trained model to predict the next step, next action. And there the requirements are low latency and high power efficiency. This enables AI inference chips to be used at the edge, for example, in automotive vehicles, in voice assistants, in smart cameras, etc. In the data center, these functions of training and inferencing are bundled in one package. So you can imagine that an AI chip with that level of complexity, the size of the AI chip cannot fit in a monolithic die. There are not only challenges of design and scale, but they're exceeding the reticle limit, which is 858 square millimeters for EUV, which is roughly 33 by 26 mm. So inevitably you have to break up your AI chip, your chip, into multiple dies. And it's not enough to break them up, they have to be interconnected at speed to maintain the performance. And there has to be enough number of wires or interconnects per millimeter of the die edge. So interconnect density becomes important. And that's where the investment and advancements in packaging technologies become critical. Never before has packaging been so important for the industry. It's a core enabler and an essential technology for the next decade of semiconductor growth, and certainly for the multi-die ecosystem. Last year in August 2024, the UCIe consortium announced the UCIe 2.0 standard, which has support for stacked dies, so improves interconnect performance, power efficiency with stacked dies, as well as support for test, debug, and manageability of silicon. This slide shows you some of the stats of the UCIe IPs. UCIe A stands for advanced package, and S stands for standard package. And UCIe A has higher performance and higher power efficiency than standard package. The way to read this slide, the numbers in the table represent terabytes per second of speed between die to die per millimeter of the die edge. And that's represented at a certain data rate, which is the left column, so for example, 40 gigabytes per second data rate, and using certain number of data lines, for example, 64 data lines. So an example would be using 64 data lines and 40 gigabytes per second data rate, you will achieve a bandwidth density of 12.9 terabytes per second per millimeter of edge. And there's significant work going on to move these numbers up northward. The other important part of the UCIe IP and interface IPs is testability, debug, reliability. So just imagine you have a large multi-die designs and it fails in the field. All that investment and cost and effort put in fails because of one critical data link that gets corrupted or it fails for various reasons. So and what if you had a solution where you detect in the field live the problem before it happens, and then you move the data to a redundant link and let the chip continue, enhancing its health and reliability. So this is referred to as monitor, test, and repair. As I mentioned earlier, high bandwidth memory is an essential requirement for AI chips. The memory wall is a significant problem. So is the I/O wall, of course, but the memory wall especially is a problem that all AI chip architects are grappling with. In the world of HBM, stacked dies is not new. You're familiar with your basic HBM architecture, which includes a number of stacked DRAMs sitting on a base die and communicating with a host die on an SoC chip via, say, an interposer. What's changing is that there is more and more functionality being added to the base die. For example, HBM5 and controller are moving to the base die. That not only boosts performance, but also frees up real estate on the SoC, which now you can add more functions to the SoC, or it reduces cost. Furthermore, HBM IOs are being replaced by UCIe, which again frees up shoreline on the SoC, further enhancing performance and power efficiency. As you all know, stacked dies offers a promise of increased performance, even additional boost to performance and power efficiency. And thanks to the advancements in advanced packaging, hybrid bonding, and there are significant other alternatives being invested in, new types of metallization. There are startups in this space. This is indeed an area ripe for investment and growth. And thanks to all that work, the future looks very bright for logic-to-logic stacking. This offers the advantage, of course, of higher bandwidth at low power, smaller form factors, reusable and scalable chiplets. And like it was mentioned in the plenary session, it now allows applications to mix and match dies thanks to the higher interconnect density. And speaking of interconnect density, hybrid bonds promise a sub-micron interconnect pitch. If you look at the microbumps, they typically stop at 10 microns. It's expected that with hybrid bonding, there's a 100x improvement in pitch and increased improvement in interconnect density. That enables more and more applications to leverage the advantage of multi-dies, where you can have the top high-performance compute die using the most advanced processes, and the lower die, which don't scale in the same way, to use an older node. Helps with reducing costs, and the flexibility is important to give you foundry capacity, etc. However, stacked dies impose complex requirements to interface dies, to interface IPs. So for example, a stacked die topology, whether it's face-to-back, where dies are stacked on each other, or face-to-face, where the bottom die is flipped to face the top die, that generates new requirements for the interface IP. For example, the 3D-enabled interface IPs like 3D-IO from Synopsys, you now have to modify them to add signal TSV escapes to bump, provide power ground, rerouting, etc. Given the complexity and size of the AI chips and large high-performance multi-die chips, traditional reference flows, EDA flows, do not scale. There is a need for a unified exploration to sign-off platform, which includes feasibility analysis even before you have RTL, partitioning, disaggregation, technology selection, technology node selection for your different dies. How do you know the impact of those choices? And I'll talk about that in a few minutes. Prototyping, flow planning, 3D for flow planning, heterogeneous integration. You're all familiar with the challenges and opportunities of heterogeneous integration. Implementation of advanced packages. It used to be that at the package level, the die-to-die routes were done by hand, right? So you generate some strips and you run them. That doesn't scale anymore because of the number of interconnects and the interconnect density, implications of single integrity, power integrity, crosstalk, insertion delays, and so on. And what's needed in this, throughout this whole EDA stack, is integrated multi-physics, talking about signal integrity analysis, thermal, EMIR, IR drop, etc. throughout the whole flow. The decisions one makes in this reference flow, the decision one makes at various stages, have a profound impact on your signal integrity and power integrity performance of your chip, of your system, on the time to design closure. For example, how do you estimate the impact of your bump planning decisions, or your disaggregation decisions, or your relative locations of your different dies, choice of technology nodes? Having that prediction of the impact of your choices with high fidelity becomes important. But that's a difficult problem to solve. The solution space is large, with a large number of parameters influencing the final outcome. And this is where AI can play an important role. Synopsys pioneered the use of AI in EDA workflows. We demonstrated the use of reinforcement learning in optimization. And we've continued down this innovation path and expanded it to multi-die, the world of multi-die as well. Today we have AI solutions for signal integrity, for connections between dies, and also from die to substrate. We have solutions for improved thermal performance as well. But last but not the least, given the complexity of these chips, manufacturing and reliability concerns become paramount. So silicon lifecycle management, throughout the lifecycle, I'm talking about in design, in ramp, in production, and in field, become essential. So in fact, the test and SLM, or silicon lifecycle management, needs for multi-die span chiplets at wafer sort and pre-bond stage, to interconnects between the chiplets, mid and post-bond stage, and all the way to the system level, multi-die system level, at the post-bond stage. At the chiplets, test access becomes important. Again, remember we're talking about problem of scale. For quality and yield, SLM for known good die, as well as performance and power optimization with SLM become essential. Signal integrity monitoring, self-test repair, like the example I gave earlier. Stack test and repair management at the system level, as well as RAS, reliability, availability, and serviceability. Reliability through in-field degradation monitoring, availability through in-field reconfiguration and repair. It sounds like magic, but the technology is here today. There's continued work going on in the space. And serviceability for remote debug and diagnosis. All of these become very important for these massive systems in a package, multi-die designs, AI chips. As with solving any large problem with significant complexity, it takes a village. And certainly it's true for the world we are in. Synopsys is part of an ecosystem. We are playing a leadership role with our stakeholders and partners to foster innovation, to invest in research and development, to improve standards and interoperability. We are working with foundries, equipment manufacturers, OSATs, test companies, our EDA and IP partners, ASIC vendors, and R&D centers like IMEC. We're developing reference flows and methodologies, validated and tested in this complex world, where we take the best-in-class solutions from Synopsys and integrate that with best-in-class solutions from our third-party partners. I want to take this opportunity to highlight two such collaborations. One is with ARM, where Synopsys and ARM have worked together to power SoC and multi-die designs based on ARM Neoverse CSS, the compute subsystems. This leverages ARM CSS capabilities with this broad IP portfolio from Synopsys, including the interface IPs that I talked about with MTRs. It leverages a full stack, AI-driven suite of EDA tools for architecture exploration, for design, implementation, and verification. It ensures interoperability and compliance with AMBA, coherent hub interface protocols. The verification paradigms and methodology support the base system architectures and others. Together, we've developed reference flows and methodologies to reduce design cycles and deliver performance-optimized ARM-based infrastructure compute on advanced foundry nodes. Synopsys collaborated with TSMC and Intel to develop the very first test chip for UCIe, the very first UCIe test chip called Pie Creek. So some of you may have heard of this. It was a watershed moment for the multi-die and chiplet world. We've continued to collaborate with TSMC on many significant areas and initiatives, and one such is the tape out of a test chip using TSMC's CoWoS advanced packaging technology. It leverages TSMC's 3D fabric technology for 3D silicon stacking with advanced packaging and packaging technologies. It uses Synopsys IPs developed on TSMC's most advanced process and packaging technologies. It uses Synopsys reference flows which uses AI-driven optimization and analysis, integrated multi-physics analysis. In the HPC market, we expect at least 50% of new chip designs in the HPC world to be multi-die by 2025. In fact, I expect all AI chips to use multi-die, if not already. Speaking of stack dies, and here I'm referring to logic stack dies, Synopsys is privileged to be working with leading edge customers who are exploring and pushing the technology to allow general purpose stack dies, logic stack dies. Packaging companies, manufacturing companies, design architects, and design companies. And we fully expect that early R&D, research and development, will transition to prototypes and production. We'll see movement in 2025. We expect the manufacturing foundry capacity to expand, more package types, integration options, and price, and significantly better price efficiency, which is important. In fact, even beyond 2025, we expect that trend to continue, given the significant attention and interest from various governments, the investment from various governments, including the US CHIPS Act. That bodes very well for the semiconductor industry. And finally, I expect technology maturity in the AI world, applying AI to this whole environment of multi-die design, verification, to accelerate product productivity, exploration, feasibility analysis, availability of 3D IP to facilitate multi-die stack designs, as well as full stack EDA solutions on a unified platform, like the solution from multi-die solution from Synopsys, which includes early architecture exploration to optimize performance, power, and thermal, rapid software development and validation with high-performance emulation and prototyping, efficient die package co-design and co-optimization, all of this with integrated multi-physics. Complicated problem, lots of parameters to optimize. Advanced high-quality silicon IP for 2.5D and 3D, for advanced packaging technologies with MTRs and LTRs. And indeed, supporting all of this is the silicon lifecycle management and health of silicon. And then let's not forget functional verification advances for this vast system. These are indeed exciting times. All of us are contributing in our own ways to advance the technology and the state of technology in this very, very essential area of multi-die and chiplets. It's essential for semiconductor growth for the next decade and for AI chips. Let's work together to make it happen. Thank you.